Hi, everybody, and welcome back to another VTSS. Today we've got Mike West who's going to present, and let me also thank Hedibert for joining us for the informal discussion. Rules of the game are we take clarification questions during the talk, and as you see in the videos, the seminar is going to be recorded, and we stop at the end of Mike's presentation, and we start with Q&A. And that's it. So, Mike, thanks a lot for joining us, and the floor is yours.
Thanks, Michaela. Well, hello, everybody, and thanks for joining us. So I'm glad to be here. The topic today is based largely around a recent paper that's in process on what I will be calling SGDLM, Simultaneous Graphical Dynamic Linear Models, conditionally linear. With a main focus for, these are standard models, with a main focus for their utility and application in putatively causal settings. So the key architect of some of this, most of the work is joint with Luke, a current fourth-year PhD student, who is here in the room. So that'll be useful later on, perhaps, in Q&A. And the paper is available on arXiv, and I'll give you more information as we go ahead. So I'm going to start with just a broad overview of the SGDLM framework, the class of multivariate time series models. They've been around, well, actually many decades, as you'll see, if you aren't already familiar with the use of that acronym. And my own work in the last, well, forever, but the last 10, 15 years has been, a lot of my time series work has been heavily focused on increasing dimension, multivariate time series, in business, economic, finance kinds of applications for various decision problems. I'm a fan of time-varying parameter models. All of our models today are conditionally linear, conditionally Gaussian. Think about state space models and Kalman filtering. But the key to what we're doing in counterfactual forecasting for causal is really understanding and being sensitive about cross-series relationships. So I'll start for 10, 15 minutes just on simultaneous graphical dynamic linear models. I noticed Louis Gruber is in the room, and he is the brother of Lutz Gruber. I don't think Lutz has got time off work to join us, but he may, I'm not sure. We had a couple of papers a decade ago now on these models, and it was really just developing really old ideas in new ways. The focus being multivariate time series, where we want to spend more time thinking hard about each univariate model for each univariate time series, and thinking about them sort of decoupled individually in parallel. But then being sensitive about the cross-series relationships and how they might change in time, and volatility modeling generally through relationships across series and multivariate volatility pattern described by a time variation in a covariance matrix, fundamental to many applications. We're very, very focused on online sequential learning, filtering, and forecasting ahead at each time point, learning from data as it comes in order to be adaptable to change, in order to anticipate change. And I got bored years ago with Markov chain Monte Carlo. And so the focus, one of the foci in the early work here was to maximally exploit theory of models and do most of the calculations with easy simulation combined with theory rather than nasty challenging Markov chain methods. So there's a couple of papers there. The applications in those papers were in portfolio analysis, and they've been adopted and evolved now and applied in a variety of other areas, particularly in economics. But they're general models, and as you'll see, they're really very old models that everybody knows about and has done for decades. So at this point, let's think about a set of time series in a vector, and let's think about each one at a time. And the example I have is in finance. So we've got 400 daily stock prices. Happens to be WFC as well as Fargo. BAC is Bank of America. C is Citibank. Some banking stocks, the first three listed. Then NVIDIA, Kroger, which is the largest US grocery store system And we'll talk more about Kroger later on. And here we are at day T, and these are the returns. So today we want to forecast tomorrow and maybe the next several days for portfolios. And the whole point about being focused on customizing is to take seriously modeling each series, without regard to the others initially. For example, for Wells Fargo, we'll have some vector of series-specific predictors. And it may be company-specific, it may be banking sector factors, etc. And then, with time series people, we may well have some lagged values of Wells Fargo and maybe one or two of the other series. And in looking at daily stock prices, we're going to have small models. We're not going to be predicting tomorrow's return based on everything in the world. So there'll be selective links from day T-1 to day T, lag predictors. And then, of course, there's the question of, well, simultaneity. If what you want to do is do your best job of predicting Wells Fargo's stock price tomorrow, and I could give you the Bank of America's stock price tomorrow, you'd want that, right? You'd probably be prepared to pay for that. I mean, can't happen, but it's a hypothetical. So simultaneous relationships are then indicated, by a few arrows pointing to Wells Fargo in the customized model for Wells Fargo. And then we go down the line and we look at Y2, Y3, and all the way down to Y399 and 400. And we do the same thing, customized models, the individual, excuse me, my cell phone is giving me a spam risk alert. Sorry about that. And so we have univariate models, and they'll be conditionally linear Gaussian models, which may depend on, each of them have their own independent variables, exogenous predictors, maybe some lags of other variables, and possibly some simultaneous connections as well. And there can be loops in these graphs. For example, Wells Fargo is a predictor of NVIDIA simultaneously and vice versa, because they're going to be dependent as stock market predictors. And as I've said, I've got 400 series here, and there's a few arrows pointing to each of the current values, but there won't be lots of arrows. And particularly in this kind of application, the connectivity, both lagged and simultaneous, will tend to be sparse. Okay, so what does that give us? It gives us a multivariate system, which is a collection, in this case, of 400 univariate equations. And they could be anything, but today they're linear Gaussian. So let's take J equals 1 for Wells Fargo in day T. The X vector here is a vector exogenous variables for Wells Fargo and lagged values of past returns that we've chosen. And phi is a time-varying regression vector on that vector. The nu, of course, is residual error, and therefore the Y term here, the designation SP means simultaneous parents. So in my example, Wells Fargo has two simultaneous parents, two of the other series that are chosen as simultaneous predictors of Wells Fargo. And these will typically then be small vectors with regression coefficients. So that's a set of simultaneous equations, which we can put in a vector matrix form, where the regression terms, idiosyncratic regression terms, give us a vector mu. So we're doing our best to predict each of the series individual in that vector. The error terms come into a vector nu, and the models assume that these are independent. So we have a diagonal covariance matrix, conditionally Gaussian, and it will have time-varying elements, typically. So the other term, this gamma y term on the right-hand side, well, gamma has to have 400 rows and 400 columns, okay? And we create that gamma simply by, in row 1, putting a lot of zeros, except where the two predictors of Wells Fargo are. So in this case, that was Bank of America and NVIDIA. So this is a big, square, sparse matrix with non-zero elements only corresponding to simultaneous relationships, and we use the term simultaneous parents for predictors. I'll give you another example on the next slide. Critically, this will be a sparse matrix. The third time I mentioned that. We're dealing with dynamic sparsity. And then the reduced form of the model will invert this matrix I minus gamma and move it to the right-hand side. And so the model for the conditional normal distribution for this 400-dimensional vector y down in the bottom corner has a regression term where the individual elements of mu get mixed up through this I minus gamma inverse. And the precision term, which represents simultaneous residual dependencies, is this precision matrix, the variance matrix inverse. And I'll speak in detail in a couple of slides to each of these terms separately to just help understand the theory and structure of these models. But I want to make this statement, I sort of alluded to it, that economists have been doing simultaneous equations for decades and decades and decades. And this is simply a representation of simultaneous equation system in structural form going to reduced form, with the caveat that everything's time varying in the parameters and there's a lot of sparsity. And that defines the class of SGDLMs pretty much. So let me give you a different example. And why is it called graphical? So here's an example we'll come back to several times today. There are 16 countries, and the data is annual, real GDP in US dollars. And this picture represents a particular set of simultaneous parents. And we're not talking about the regression part here. We're just talking about dependencies within each year. And I'm going to focus on USA, Britain, and Australia down here at the bottom. Let's just look at the arrows to the US. So Britain and Australia have arrows pointing to the US. Okay, that means that Britain and Australia are parents of the US, and we called US the child of those parents. So this gamma matrix in this case is 16 by 16, and here's a picture of it at a snapshot in time. This is 16 by 9 because 7 of the columns happen to be 0, so I've just left them off the graph. And the white indicates 0, and the colors with numbers indicate what I earlier called these gamma terms. So let's look at US, Britain, and Australia. In the row corresponding to the US, there are 2 non-zero coefficients on Britain and Australia, and the rest of the values in that row are 0. And the other columns are all 0 that I've omitted just for presentation. So row by row here, we see, for example, if we look at the top, Germany, the first row is the first series. GDP is predicted by GDP in Belgium, USA. It happens to also be predicted by a little bit in Australia, in Austria, but it was so small that it was epsiloned out of the picture. So that, just go back to the equation, that structural form of the equation that here with this gamma matrix, it in the gamma part, it corresponds to a graphical representation in terms of a directed graph. That's why we use the term graph. And we use some graph theory coming along. And I'll note in this little group of 3 countries, Britain, US, and Australia, that the arrows incident to Britain, for example, come from Austria and the US. So Britain is simultaneously a parent of the US and a child of the US. So we can have cycles in this directed graph. It's not illegal to do that. We'll speak more about this example in detail as we go through the morning. I want to talk a bit about the structure of these models. So this is the reduced form. Let's look first at the implication. Remember this mu vector, element by element, it's series-specific regression prediction. And this I minus gamma inverse matrix mixes that up. It produces crosstalk in the prediction. So here's an example. The picture here is from a particular example of gamma in the bottom right. The implied inverse of I minus gamma looks like the top left. The blue is non-zero, the white is 0. It's always going to be very sparse relative to gamma, sometimes full. And so let's look at this I minus gamma inverse term and expand it, give it its binomial expansion. And in the equation for y, this I minus gamma inverse term hits mu. So the identity just picks up mu. The gamma term, the second term of the sum, is gamma mu. So that is linking elements in the mu vector from the parents of series 1 as predictors of series 1. Okay, so how well you predict Bank of America is important in how well you predict Wells Fargo, because Bank of America is a parent of Wells Fargo. And then gamma squared goes out to the grandparental predictors. So we've got, let me say, Morgan Stanley here is a predictor of Citibank, but not a predictor of Wells Fargo. Citibank is a predictor of Wells Fargo, therefore there's an inheritance through the generation. And how you point predict, I forgot the bank I named, the grandparent, how well you predict the grandparent feeds through to the grandchild. Typically, as you go to higher generations, these terms go to zero. The powers of gamma go to zero, and we can talk more about the mathematics and why. Let's now look at the residual part. So the inverse variance matrix, the precision matrix, some people call it the concentration matrix, has this form, capital omega. So in this example, it's a positive definite symmetric, very sparse matrix. It will have non-zeros on off-diagonal elements corresponding to conditional dependence. I think we all know that in the multivariate normal. And let's look at this term then and explore it. So this nice mathematical form in the top right, if we just expand the quadratic, remember that lambda t here is diagonal. So that doesn't do anything on the off diagonal. These two terms introduce non-zero elements, blue spots, in off-diagonal elements for parent-child pairs. So in our running example, in the row and column corresponding to Britain and USA, there'll be a non-zero, and in the column and row. In the row and column and row for Australia and USA, there'll be a non-zero. Okay, that's natural. Parents are related to their children. The interesting quadratic term here introduces what we call moralization effects. And if you're familiar with the graph theory terminology, you'll know about that, but some of you may not be. Well, let's look at this triptych again. USA has parents Britain and Australia. So USA is a child of Britain and Australia, but they're not married. So it's an illegitimate relationship. And we make it moral. It's an immoral relationship. We make it moral by joining up Britain and Australia. And what that means in our example is that inserts an off-diagonal non-zero in the precision matrix, a conditional dependency between Britain and Australia because they're linked through their common child. Okay, so this is the structure really in a conditionally linear Gaussian SGDLM that helps us understand the graphical structure, how series are related both in terms of the crosstalk in their point predictions in the previous slide, and then their relationships in the residual through the precision. Okay, methodology, how do we fit these models? Well, if we stack the independent variables and lag predictor X along with the simultaneous predictors Y in a vector F and their corresponding dynamic regression vectors in a vector theta, we've got a dynamic linear model for Y. Each Y has a univariate DLM. Okay. And we can utilize the standard theory, Kalman filtering with frills on each of those models in parallel at each time point. And those of you that are familiar with the Bayesian literature on state space models will know that one of the frills is easy, tractable Markov dynamics for time varying volatility. Okay? The point here is we've got standard analytic, trivial computational methodology in these models. If we were to exploit that in the SGDLM analysis. So the way it works is that at each time point, moving ahead one time point, we're looking at using that theory for analytic linear Gaussian evolutions, normal gamma distributions for the filtering updates. And we can do that parallel across series. So its computation is linear in the number of series. But then taking care of the simultaneity, that's where simple Monte Carlo comes into play. We can use the theoretical models on the univariate series separately as distributions to sample from and evolve in the future through direct forward simulation, and then use importance sampling to make the corrections to give those samples weights so they're not quite equally weighted, to reflect the fact that we have this simultaneous set of connections. It's a whole other talk, but it's easy to do that, to generate tracks into the future, sample paths of the state vectors and the volatilities that underlie then the ability to generate forecasts of the outcomes Y. I like the term synthetic futures. And part of this exploits the fact, and we'll come back to this, that the 1 step, 2 step, 3 steps ahead forecast distributions conditional on all of the parameters are Gaussian. Therefore, mixing over the Monte Carlo samples of parameters turns them into mixtures of Gaussians. Easy to analyze, easy to simulate. At each time t, we've got a condition on the observed data when we see it, do the filtering updates, and we use variational Bayes there to take the Monte Carlo representation back to a conditionally conjugate analysis to continue into the future. There's a lot in our earlier papers on how this is a self-monitoring exercise. And the sparser the model is in terms of gamma, the sparser gamma is, the more accurate this becomes. In the limit, if gamma is diagonal, this is theoretically exact. A lot more to say there. We're building on that as we move to a counterfactual setting. And a main goal here is then the extension of the existing SGDLM methodology for this counterfactual setting, which introduces complications basically involving missing data. So let me go back to our GDP. Why am I interested in that GDP graph and the context? Over the years in the causal inference literature in economics and political science, one little example has been German reunification at the end of 1990. And the question there was, in terms of per capita GDP, what was the effect of reunification? You know, Germany absorbed, it increased its population dramatically, and it absorbed the implication of taking care of rehabilitating post-Soviet industry, basically. So what is counterfactual forecasting all about? It's become associated with the idea that, in this example, for instance, at 1990, we forecast ahead over the next several years. So the green shading and dashed line represents forecast distributions in the future made at the end of 1990, on the assumption that what we had learned about prior to 1990 made sense. We're conditioning on the model fit to pre-1990 data. The X's happened to be what the outcome was with German DDP. It was depressed. A couple of years it didn't look so bad, but then cumulatively it was depressed over the following decade or more. Now this is in a system with, you know, all of the other countries. So this comes from a multivariate analysis where one is interested in using post-1990 data as you move through the post-1990 period to continually update and learn about what the impact has been. Another example, I mentioned the Kroger stock on the stock return slide. I work with 8451, which is a large data science company, wholly owned subsidiary of Kroger, which, as I mentioned, is the US's largest pure grocery store system, and it's big. So I first got involved in the counterfactual forecasting a couple of years ago with them after a series of projects on a variety of topics. And so any retail context, is involved in the business of trying to make more money by fooling the customers into buying more with various promotional campaigns. One of the favorites I love in one of our local stores that's in the Kroger system is now and again they'll have a buy two, get three free offer. So for the price of two, you get five. And sometimes they have these offers on things good coffee that I like. And so one is interested in the question of a particular campaign or a series of campaigns, a particular set of promotions that could be on a particular brand of coffee, or they could be in the whole grocery department. They could be a store level or a regional level involving various stores. And of course, what's interested in to the company is, as you move through time into the experimental period with the promotion, how is it working? Is it working? Decisions to stop it if it's not, decisions to expand it to other stores if it is, etc. So causal forecasting there is de rigueur, absolutely a driver of a lot of what they care about. I know some of you are not from the US. I know that although Michaela is not in London at the moment, some of you may be from the UK and familiar with Tesco. Tesco is, so every large company that sells anything has the same questions, but in the grocery system, Tesco would be comparable to Kroger. It's got many more stores. It doesn't make it doesn't make as much money per store. That's partly because Tesco has lots of little stores. But the same general questions arise worldwide. Here's a snapshot of some data from a Kroger study that we published. We see in the bottom left some states, including North Carolina. Most of it was in Tennessee, Georgia, and Virginia. The purple dots are stores that didn't have a particular campaign. The yellow dots were stores where the campaign was applied. So it's control and treatment sort of design. The size of the circles simply represents the revenue, average revenue on a weekly basis. And the series above, you see over the years, the fluctuation in weekly revenue by what designated control and treatment stores. We use the term treatment for the stores that played out the campaign. And the vertical gray lines show you the period of weeks where the campaign was running. So the question here is, at the beginning of the campaign, begin monitoring and ask the question, is it working? How is it working? Store by store and across the system. So it's a problem of control and causal inference in essence. So characteristics and goals of such studies, before you start a campaign, so I'll use the term intervention, with the GDP, that was reunification, a German reunification. With the Kroger system, that was the start of a campaign. Pre-intervention, you've got data, you can learn from that, you can build models. You can use exogenous variables, you can build whatever models you like. And the point there is to understand and quantify the structure of the multivariate system. Then at the point of intervention, you have this sort of bifurcation. The series get broken into two. Some are controlled, some are treated. Sometimes it's a purely observational intervention. We didn't choose to reunify Germany by design. It happened, it was a political event. Sometimes it's a designed experiment. We have to have controls, and there's an important assumption that when we designate some series as controls, that it's a leap of faith that whatever happens as a result of the intervention, if there is a causal effect on some of the treated series, that the designated controls are not impacted by that effect. And that's an important thing that people always assume it, but rarely get into the business of assessing it. And we do a lot to assess that. And the effect could be direct. For example, there could have been an effect of a supermarket that didn't have a particular promotion of coffee, cheap coffee for a couple of weeks. It was across town and they didn't have the promotion, so all of their customers bought coffee at the other store. Okay, so that's a case where the intervention does impact controls. The literature uses the term synthetic controls a lot. for made-up controls, and typically what they do there is driven by technicalities. For example, if they've got a lot of series that are controlled, they'll take a weighted average of them to use as a single control. But that's historically primarily been driven by computational, technical reasons rather than holistic modeling reasons. Then following intervention, we get into the counterfactual phase, where we follow the data from the control series as observed data, and we continue to learn about the structure of the model from the control observations. But the counterfactual setting is that we maintain the model structure as it was at intervention and don't use what happened to be the realized outcomes on the treated series to update. So we're making the assumption that the control series are evolving in time, and what we think about the relationships between the control and the treated series is based on the pre-intervention structure. So that's important to get that as right as possible. So that's the setting of a sequential time series intervention study with a counterfactual analysis. So on that last, well, quick question. So here we are. This is German GDP. I've morphed the data, transformed it to annual changes. And the first picture is simply showing the data, annual changes in German GDP up until 1990. Then the shading and the median and 90% interval forecast at 1990 for the next several years. And what actually happened was quite a bit lower. Okay, so that's a counterfactual forecast multiple years ahead. And if you want to then do causal inference, then the tradition is that you simply subtract the shading and the median line from the actual data. So just shift those distributions down in this case and define that as the causal outcome in a predictive sense. And then as you go through time, a few years later, 7 years later, we're continually updating based on all of the other series that are treated as control. And that is getting revised and revised as we go through time. Okay, so here's a picture of that from one of our published Kroger examples, where we had a large number of series, 2 recent papers, well, a couple of years ago now. So this was then aggregating up across individual stores. I showed you a picture with 50 or 80 stores. And we're looking at stores within regions, the Atlanta region, the Dallas region, the Atlantic Coast region, and the southern region, Mississippi. And here the aggregation to actual revenue is translated into percent lift, i.e. what is the difference between the outcome and the counterfactual forecast as a percent of revenue. And you can see, there's a couple of percent lift in Dallas and Atlanta, maybe 5% in the mid-Atlantic. But the promotion didn't seem to work at all, and maybe it was slightly negative in the southern region. Okay, so these are the kinds of summaries that we want to get out of these models. There's a couple of papers there that articulate this and give nice introduction to the general area of causal forecasting, actually. But for us today, it's just a stepping stone, because the models we used there were very traditional multivariate dynamic linear models, which, as some of you will know, have some constraints, have technical theoretical constraints which limit their flexibility. They don't allow customization of individual univariate models. Some of you will have heard the term common components models in other areas of econometric time series. So part of our interest, with the SGDLMs is to move the methodology ahead by expanding the pools of models that we have available. So let's get some desiderata on what we want. Full uncertainty characterization in forecasting is a given. We're all Bayesians today. We're particularly interested in scaling with larger numbers of potential series as controls in particular, but potentially many treated. For example, in the supermarket system, we get promotions which will have hundreds of controls and hundreds of treated series that are running the campaign. The whole focus on sequential time adaptivity is so important, because monitoring a promotion campaign in supermarkets, store managers and regional managers, they don't want to continue to lose money through a promotion if it's not working. And if it's working, the regional managers and the national managers want to play it out in other stores. So the whole business of doing things sequentially to inform decisions is a real key. And then, as the example I alluded to showed, sometimes we're dealing with a multivariate series and we want to aggregate up, to a national level, say, with supermarkets. So having access to easy simulation of the individual series collectively that you then just do arithmetic on, that's pretty much a very important desideratum in scalability. And so I highlight some of these goals. I mean, some of them are satisfied by other models, but I highlight them because it just so happens that SGDLMs, naturally address these desiderata. So let's go there with the German GDP series. There's the GDP on a log scale of 16 countries, including Germany. It has the thick black line. How do we think about what happened after 1990? Well, most of the publications, there's a handful really only in the economic causal literature, analyze log GDP or GDP itself, which is kind of crazy because it's all in the common trend. We analyze the annual changes, okay, the returns on GDP, if you like, where you see the structure. And in particular, you see in 1991, 92, and then a big 93 dip in Germany and several of the other series. Those of you that are old enough will remember there was Europe and the US, there was a recessionary couple of years there that was confounded with the reunification events in many ways. If somebody is interested in what the blue and the purple curve are in 2000 and then in 2000, and I think that was 2003, you can all probably guess what they are, but we'll come back to that later. The blue country and the purple country. Actually, there's a test there. Figure out what they are. Huge increase in GDP in 2000 for the blue country. Huge decrease in GDP in 2003 for the purple country. Okay, so the setup we have then is, as I mentioned earlier, people had used raw GDP and taken an average of all of the other countries as a single control. I worry about that because that averages GDP in Austria, France, Belgium, Netherlands, Denmark, major trading partners, particularly Austria, major trading partners of Germany. So wouldn't you want to worry about the interference effect I alluded to earlier, that these countries would be impacted if Germany were? So we do something a little different. First of all, we look at the rational changes in GDP on a log scale. And we take 14 countries as experimental, as treated, and only 2, Australia and New Zealand, as controls, on the basis that if there was some interference, Australia and New Zealand are going to be least likely to be impacted. And when we look at the data historically, the changes were the smallest there anyway. And I'll make the point that in the causal time series literature, which is only just beginning to get multivariate, people are still looking at bivariate series with a single control. So the scalability here is quite in advance, and SGDLMs allow that. Okay, but the existing methodology of SGDLMs doesn't allow missing data. And so what we have here is that the treated series post-intervention are missing data. The controls observed, the treated are not. And it's particularly complicated because in the SGDLM, some of the series that are now designated treated may be required as predictors, as parents of others. Okay, and we fix this just by doing Bayesian analysis. If something is missing and you want to know what it is, you figure out what are the relevant conditional distributions to use to infer it, and in a simulation analysis to sample. And going through time then, at each time point, we have conditional distributions that are conditioned on control data that are used to then simulate the relevant conditional distributions for the treated data under the counterfactual assumption. And this gets updated as we move through time. In two little paragraphs, that's 75% of Luke's thesis. So it's easy to say. And there's some real advances that have been made there. And the advances are based on the theoretical structure of the existing methodology. I mentioned earlier that forecast distributions in the Monte Carlo analysis are theoretically mixtures of large numbers of conditional Gaussians averaging over the Monte Carlo sample. And we maximally exploit these analytics to apply to the counterfactual setting. Okay, so let's work through a bit of an example. There's the graph I showed you earlier that represents the simultaneous parents. And some of you might realistically naturally ask, well, where do you get the graph from? Here's another graph that represents a different SGDLM. Each one is an assumption. Who is predicting whom simultaneously? And this one in the lower left is a bit busier. There are more arrows. It's a bit more complicated. And there are lots of possible graphs. So the graph, in a sense, is a nuisance parameter. So how do we address that? Well, we do a little bit of Bayesian analysis. In the pre-intervention data, you can look at lots of possible graphs. And it's nice in an SGDLM because here in this example, we've got 16 linear regressions. And you can look at them each individually. Dynamic linear regressions, dynamic linear models. And you can search in various ways over possible graphs, and stochastic search of various kinds can play in. But it's nice because you break it down to univariate dynamic linear regression. You would generally want to have penalization for complexity. Nobody wants all of the arrows in this graph. And traditional sort of sparsity priors give you complexity penalties. And so that's basically what we do. And then the SGDLM analysis runs through the pre-intervention period on a collection of graphs that we select, not all possibilities, because you can't do that. And through the pre-intervention period and then into the post-intervention period, you can do Bayesian model averaging to deal with uncertainty about what the underlying set of arrows really is. This involves, in the post-intervention period, under the counterfactual, again, exploiting the SGDLM theory in new ways, because you've got a prior with some sparsity penalties on any particular graph. So if you've got 1 million graphs, you've got a prior probability on each one. You multiply those prior probabilities by the likelihood based on the data for each of those graphs. We call it the marginal likelihood because it's integrated out the time-varying parameters. And to do that calculation, we need some new theory. And again, we exploit the analytics of mixtures of conditional Gaussians to do. So that's a big extension, actually, of the SGDLM analysis, not only for the counterfactual forecasting, but also to deal with the inherent questions of uncertainty about graphical structures. Okay, so just to get into the example, I'm going to spend much of the last 15 minutes on the example, but I've got one more sort of methodological development to talk about. I call this nowcasting because some of you are economists and we know what that means. So here's the results of such an analysis where we're nowcasting, and the green line here is a current median, and the green shading is a current 90% posterior interval at each year. And this is sequentially updated through time. So this is filtered inferences. There's no looking back. Pre-intervention, this is based on all of the data. But the interval and median indicators there are based on forecasting each year based on only the control data in that year. And then we move into the post-intervention period. And of course, we don't know Germany. We don't know Britain. We only know Australia and New Zealand. So all of the forecast information there is under that counterfactual. And you can see the intervals getting slightly wider just about. But this bears out the point that German GDP was way down. 1993, it bombed. 91, 92, 93. And then it sort of came back a little bit, but maintained its low value under the counterfactual. Austria is probably the most impacted of the other 13 treated series. And you see it's down too, although perhaps not quite as bad as Germany, and the UK too. And these are just three examples drawn to illustrate the counterfactual forecasting. The UK sort of comes back, but over the years, you see a sort of systematic over-forecast under the counterfactual. When you accumulate up and exponentiate on the control scale, you can see, very, very, very dramatic underperformance of the German economy in this GDP metric relative to the counterfactual forecasts. In the first 2 years, it doesn't look so bad, but then the 1992 and 3 kick it down a lot. So what about causal inference? What does that mean? I mean, that picture said, well, things were down relative to the counterfactual. If you believe that the only thing that happened in 1991, 92 in the worldwide economy was due to German reunification, then you're done, okay? Lots of other things were going on there. As I mentioned earlier, there was not a worldwide recession, a European and US, largely the Western world recession in 91, 92. And the impact of that was felt in 93. And it was obviously magnified in Germany by the cumulative effect over the first 2 years post-reunification that Germany was feeling in rebuilding East German industries. So to get a bit closer to this, a bit more formal about this question, we've introduced what we call the outcome adaptive model. CFM stands for counterfactual prediction. OAM stands for outcome adaptive. And what this is for is to get a bit more serious about formal Bayesian counterfactual, formal Bayesian causal inference. Inherently, a counterfactual standpoint is a null hypothesis. We're going to continue to forecast under the assumption of no change in the designated treated series. That's a null hypothesis. Well, Bayesians, to do inference properly, to assess a null hypothesis, we need an alternative. In this case, there's only one global alternative, that something happened, okay? No change or some change. And that's all the outcome adaptive model is intended to do, okay? So let me go back to the supermarket sales example, different data set. This was a campaign played out on the weekly scale here. At week 32, there's a vertical dashed line. It's revenue in a retail sales context from a particular area. And we've got 30-some weeks of pre-intervention data and 15 weeks or so of post-intervention data. The realized revenue is in red, okay? And you can see it takes a jump following the intervention. There are two control series, black full and black dash, and you see they're pretty much unimpacted. They're pretty much the same in terms of general levels of variation after the intervention. So they look like retrospectively look like good controls. Pre-intervention, the green line is the one step ahead forecast median of revenue, and it does a pretty good job of forecasting the actual red revenue. And it's 90% intervals, pretty well cover the outcomes. Then post-intervention, the counterfactual forecast is in blue. So the post-intervention counterfactual forecast of the red line is this blue line. You can see it's continuing in line with pre-intervention. It's the null hypothesis that nothing changed. Whereas the red data is screaming, hey, this intervention, after the time of intervention, we've roughly doubled sales. Revenue has gone up dramatically. So an outcome adaptive model, the green line is forecasting the data much better. I'll tell you exactly how it's constructed. By the way, the intervals give you some notion of uncertainty. There's a lot of uncertainty. But the point here is the counterfactual is a null hypothesis saying everything's the same as before. So we're going to one step ahead forecast. We're going to continue. Whatever the control data was doing there, it wasn't saying revenue is going to increase because the control series were not increasing. Whereas the outcome adaptive model was able to do a better job one-step forecasting going ahead. So what is an AOM? Well, it's the same model. It's the SGDLM, just running forward in the post-intervention period as well as pre-intervention. Treating the experimental series data as real data, updating week by week or year by year. But critically, at the point of intervention, at the point of the campaign beginning, a modification is made to allow increased uncertainty on the parameters of the model components for the treated series. So that then allows the post-intervention data to be more influential. It's a traditional idea in time series intervention analysis. So there it's going to be more adaptive post-intervention. It's going to predict the data, fit and predict the data better. But importantly, it gives a comparison. It gives a formal comparison. It gives you the global alternative to the null hypothesis of the counterfactual. So your inferences can be directly compared. And if you're doing simulation analysis, as we are, that's just simple arithmetic to do that. The other point here is that, again, in this retail sales example, after 3 or 4 weeks, the managers are saying, hey, well, this promotion is really working. It's doubling our revenue. So let's play it out in all of the other stores. Okay. And at that point, it's the outcome adaptive model that becomes the relative model, the relevant model to continue to use into the future. The counterfactual model gets discarded. So on the formal inference here, then, in causal inference, it's typical to use the term causal estimand. And this is, it's simply prediction, in my view. So if we run the outcome adaptive model AOM in parallel to the CFM, in this case, in the GDP post-intervention, and look at the regression components in each of those models, in terms of the parameters, the means of those two distributions, and then average over the Monte Carlo samples and take the difference, then that is the Bayesian, full Bayesian estimate and its uncertainty of the causal effect under the assumption that the controls were not impacted by the intervention. And we'll see the minus 0.05 on the difference log scale here for Germany is pretty persistent across the decade or more after the intervention. Less severe and more uncertain, of course, in Austria, about half the level in terms of its global reduction, and about the same in the UK. The UK does show this I mentioned this recession in 91, 92. The UK shows this up much more, in fact, than Germany and Austria and some of the other countries. Unrelated, I believe, to what was happening in Germany. It was the result of other expansionary activities in the Western world. So the point here, for those of you that do causal inference, is that this is full causal inference. We're not just looking at how the data disagree with the null hypothesis. We're looking at comparing it with the alternative hypothesis of something changed. And we can dig into that. I'm looking at the time here. So let me skip through this. This is simply showing that the AOM can make different inferences. I can come back to that. This is looking at another aspect of the model. But in view of the time here, it's a little ambitious. I want to spend just a couple of minutes on this because I know Hedibert's got things to say about dynamic factor models, as arguably, well, I know Sylvia joined us as well. I think we have 2 of the world's 3 or 4 leaders in dynamic factor models in the audience. I want to come back to SGDLMs and in the reduced form. So we've got individual predictive components in the elements of mu. We've got the crosstalk contemporaneous relationships through this large sparse matrix gamma. It's a multivariate system. And now what I'm going to do is something we all know about, is I'm going to apply a decomposition to gamma. I'll use the singular value decomposition. So L is a matrix with orthonormal columns. S is a matrix with orthonormal rows. D is a diagonal matrix of non-zero singular values. And if gamma is sparse, L and S will typically be sparse. And some of the eigenvalues, the diagonal elements in D, will be 0. So that represents a dimension reduction. So let's just plug that gamma into the equation for Y and define this vector eta t as I've got there. And understanding that some of the diagonal elements of D will be 0 in sparse cases, the dimension of S will reduce accordingly. Typically, the effective dimension of eta will be less and potentially a lot less than the dimension of Y. And this equation involving eta, it's a dynamic factor model. So we've taken the graphical model structure that gamma defines and shown that it implicitly has inside it a dynamic factor model. And as I mentioned, typically in sparse cases, L, the factor loadings matrix, and S, typically called the score matrix, it's the matrix that maps Y to the factors. They'll be pretty sparse when gamma is sparse. And there's a nice tie-up. There's some graph theory here that's largely due to Luke, the co-author on the paper, that aligns the parents in the graph that I mentioned earlier, the parental predictors, with the factors. And there's a lot of complexity there, but there's some nice theory there that highlights the linkages between graphs and factor models. And in application, I'll spend the last few minutes back to the GDP, it can generate some insights. For those of you that are interested in graphical models and factor models, I, for 30 years, have worked on both. And I've often been a bit concerned that they represent different approaches to dimension reduction in modeling, different approaches to putting zeros in large matrices to structure models according to data. And this, I like it because it's a nice marriage of the two. It shows that graphical models are in fact factor models. So what does this look like? Here's a picture like the one I showed you earlier, where the response series are on the vertical axis and their parents are on the horizontal axis. This is the reduced version of gamma, deleting the 0 columns. And so the L and S look like this in this case. The reduced dimension takes us to 7 factors. And you'll see in the S matrix, the first column is Germany. So the first factor is a cleaned up version of Germany. Germany is its local regression and trend plus noise plus the first factor. Second factor is similar for France. And then Britain and Australia here. Remember, Britain and Australia are parents of the USA. So they are common parents of at least one other series. And they are defining the third factor collectively. Okay, so this is nice tie-up between common parents of one or more child nodes in the graph with the labeling of factors. So we could call the first factor, if you like, the German factor, the second factor, the French factor, the third factor, the Britain, Australian factor, and so forth. Let's pull out a couple of factors. So we do, the analysis generates Monte Carlo samples of everything, and it's easy with some identification questions addressed to look at factors. And factor 1, arbitrarily labeled factor 1, is the German factor. And we can see that after reunification, it drops 1, 2, 3 years in a row. And then it restores itself to a pretty constant level. So we can imagine it is confounded with other things going on in the early 90s, but we can imagine that as pretty significantly representing reunification. If we look at factor 5, this is a factor that's based on the common parental sets, Belgium, USA, and Australia. It's one of 3 factors that these 3 series define. Yeah, this factor drops a bit for a couple of years to 93, but then it comes back pretty much to the levels of the 1980s, certainly not to the 1970s. So we'll see that maybe the reunification impact is not showing there. It's largely accounted for by the German factor. The factors have variation over time, and we can look at different contributions, but I'll leave that for possible questions. Last slide is just pointing to other applications. I'll mention that because some of you may be interested in other applications. I'm not going to get into that, but in the US, it's a very topical political economic question of massive investment of taxpayers' money into public health care. And is it working? Does it impact other things such as the well-being of the workforce in different ways? But I'll skip through that slides because I'm done with time. and remind you who's responsible for a lot of this. It's Luke. We've had the paper on archive for a few months. We're just getting close to a fairly substantial revision. It's going to go out there very soon, and you can follow that up if you like. We'll have a follow-up case study with Medicaid data very soon, actually, as well, to go on archive. And I'll invite you to go to the website. This is my personal website where you can find links to the stuff that's up on archive. And also at the start, I mentioned 2 or 3 other papers on our first forays into causal forecasting using multivariate DLMs before we realized that it's going to be much better to do it with SGDLMs from here on. So run over a couple of minutes. Thanks for your time, and happy to chat about anything anybody wants to raise.
Thanks, Mike. Absolutely. Great talk. So stop.